Good evening, engineers. It's amazing to have you guys here. I can see that a number of you have been, yeah, you're quite on time, and that's commendable. My name is Captain Blesius Chelimo, a highway engineer from Kenya, and a member of the Roads Up team. We are really honored to have you here today, and I just want to welcome all of you, and thank you for sparing a few minutes to learn and grow with us. So, as you're waiting for more members to join us, I will share a short video with you guys. So, I'll be sharing the video right away so that you can, the few of you that are in the meeting can watch it, and maybe you can share the takeouts from the video after I'm done sharing. After that, I'll introduce or allow a few of you to say hi to us because it's an honor to have you guys, and it's just it's in order to give you a chance to say hi to the Roads Up team and the other engineers in the meeting. So that will be the order. Then after that, I will allow our lead engineer James Murithi to take us through the horizontal alignment masterclass. So you guys stay tuned. This is going to be amazing, and I'm going to share the video right now. Please kindly confirm if you can see my screen. Kindly confirm if you can see my screen. And also, someone will just unmute and confirm if you can hear the sound from the video kindly.
Laying out a new roadway seems like a simple endeavor. You have 2 points to connect and you're...
Is it audible?
Yes, audible. Thank you.
Thank you so much, engineers. All right, let's watch the short video, then we can share the takeouts as we interact. Thank you so much.
You're trying to create a simple, efficient path between them. But there are lots of small decisions that make up roadway design, nearly every one of which is made to keep motorists safe and comfortable. Although many of us are regular drivers, we rarely put much thought into roads. That's on purpose. If you're thinking about the roadway itself at all while driving, it's probably because it was poorly designed. Either that or you, like me, are just innately curious about the constructed environment. If you put it in the context of human history and evolution, it's a remarkable thing we're able to put ourselves in metal boxes that hurtle away at incredible speeds from place to place. It's not entirely safe, but it's safe enough that most of the world chooses to do it on a regular basis. And the place that level of safety and comfort starts isn't immediately evident to the casual observer. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about roadway geometrics and the shape of highways. This video is sponsored by Ting Wireless. More on that later. Designing a road is like designing anything complicated. There are a multitude of conflicting constraints to balance and hundreds of decisions to make. In an ideal world, every road would be a straight, flat path with no intersections, driveways, or other vehicles at all. We could race along at whatever speed we wanted. But reality dictates that engineers choose the maximum speed of a roadway based on a careful balancing act of terrain, traffic, existing obstacles, and of course, safety. If you're going to sign your name on a roadway design, and especially if you're going to choose a speed motorists are allowed to travel, you have to be confident that vehicles can traverse the road at that speed safely. That confidence has everything to do with the roadway's geometry. You would never put a 60 mile per hour or 100 kilometer per hour speed limit on a city street. Why? Because hardly any competent driver could navigate a turn that fast, let alone avoid a hazard, maneuver through traffic, or survive a speed bump. So how do we know what kind of road features are manageable for a given speed? There are three main features of roadway geometry that are decided as a part of the design: the cross-section, the alignment, and the profile. And there are fascinating details involved in each one. The first one, cross-section, is the shape of the road if you were to cut across it. The roadway cross-section shows so much information like the number of lanes, their widths and slopes, and whether there's a median, shoulders, sidewalks, or curbs. One thing you might notice looking at roadway cross-sections is that they're almost never flat. The reason is that a flat surface doesn't shed water quickly. This accumulation of water on the road is dangerous to vehicles, making roads slippery and creating more ice in the winter. So, nearly all roads are crowned, which means they have a cross slope away from the center. This accelerates the drainage of precipitation and keeps the surface of the road dry. But not all roadways are crowned. There's another type of cross slope that helps make roads safer. In curved sections, engineers make the outside edge higher or super elevated above the center line. This is also to help with friction. Any object going around a curve needs a centripetal force toward the center of the turn. Otherwise, it will just continue in a straight line. For a vehicle, this centripetal force comes from the friction between the tires and the road. Without this friction on a flat surface, there would be no way to make the turn at all. For example, if I roll this ball down a flat roadway, it's not going to go around the corner of the road because there's no traction. Rubber tires provide this traction against the road surface, but it's not entirely reliable. Rain, snow, and ice significantly reduce friction. Different weights of vehicles and conditions of tires also create variability. Rather than design every curve for the worst case scenario, it would be nice not to have to count on tire friction for this needed centripetal force. Super elevating a roadway around a curve reduces the need for tire friction by utilizing the normal or perpendicular force from the pavement instead. In my demonstration, if I get the bank angle just right, the ball goes around the corner perfectly, even without any lateral friction with the track. Banking roadways also makes them more comfortable because the centrifugal force pushes passengers into their seats rather than out of them. If the super elevation angle is just right and you're traveling at precisely the design speed of the roadway, your cup of coffee won't spill at all around the bend. Super elevation also helps reduce rollover risk by lowering a vehicle's center of gravity. If you pay attention on a highway, you'll notice that the cross slope changes direction on the outside of curves, and you go from a crown to a super elevation. The faster the design speed of the road, the higher the bank around the bend. The shape of curves themselves is the second aspect of roadway geometry I want to discuss. Just like super elevation, the radius of a curve has a significant impact on safety. The tighter the turn, the more the centripetal force needed to keep a vehicle in its lane. Crashes are most likely when radii are small, so engineers follow guidelines based on the design speed to make sure curves are sufficiently gentle. It's not only the curves that need to be gentle, but also the transitions between straight sections. At first glance, connecting circular curves to straight sections of roadway looks like a perfectly smooth ride, but forces experienced by vehicles and passengers are a function of the radius of curvature. So, if you go directly from a straight section, which has an infinite radius, to a circular curve, the centrifugal force comes on abruptly. Another way to think about this is by using the steering wheel. Every position of your wheel corresponds to a certain radius of turn. If straight sections of roadway were connected directly to circular curves, you would have to turn the steering wheel at a transition instantaneously. That's not really a feasible or safe thing to ask drivers to do. So instead we use spiral easements that gradually transition between straight and curved sections of roadway. Spirals use variable radii to smooth out the centrifugal force that comes from going around a bend, and they allow the driver to steer gradually into and out of each curve without having to make sudden adjustments. Even with all those measures to make curves safe and easy to navigate, drivers still usually have a little bit of trouble staying centered in a lane around a bend. This is partly because tires don't track perfectly in line with each other when turning, especially for large vehicles like trucks, but also because the forces are changing and that takes compensation. Because of this, engineers often widen the lanes around curves to provide a little more wiggle room for vehicles. This happens gradually, so it's relatively imperceptible, but if you pay attention on a highway around a curve, you may notice your lane feeling a little more spacious. One other important aspect when designing a curve comes from the simple but crucial fact that drivers need to see what's coming up to be able to react accordingly. Sight distance is the length of the roadway required to recognize and respond to changes. It varies by driver reaction time and vehicle speed. The slower you react and the faster you're going, the more distance you need to observe turns or obstacles and decide how to manage. Sight distance also varies by what's required of the driver. The amount of roadway necessary to bring a vehicle to a stop is different than the amount needed to safely pass another vehicle or avoid a hazard in the lane. Even if a curve is gentle enough for a car to traverse, it may not have enough sight distance for safety due to an obstacle like a wooded area. In this case, sight distance will require the engineer to make the curve even gentler. The final aspect of roadway geometry is the profile, or vertical alignment. Roads rarely traverse areas that are perfectly flat, instead they go up and over hills and down into valleys. Engineers have to be thoughtful about how that happens as well. The slope or grade of a roadway is obviously essential. You don't want roads that are too steep, mainly because it would be hard for trucks to go up and down. You also want smooth transitions between grades for the comfort of drivers. But on top of all that, vertical curves also have the same issue with sight distance. Crest curves, the ones that are convex upwards, cause the roadway to hide itself beyond the top. If you're traveling quickly up a hill, a stalled vehicle or animal on the other side could take you by surprise. If that curve is too tight, you may not have enough distance to recognize and react to the obstacle. So, crest curves must be gentle so that you can still see enough of the roadway as you go up and over. Sag curves, the ones that are concave upwards, don't have the same issue. You can still see all of the roadway on both sides of the curve, or at least you can during the day. At night, things change. Vehicles rely on headlights to illuminate the road ahead, and sometimes this can be a limiting factor for sight distance. If a sag curve is too tight, your lights won't throw as far. That has the effect of obscuring some of your sight distance, potentially making it difficult to react to obstacles at night. So, sag curves need to be gentle enough to maintain headlight sight distance. Of course, there are different equations for all these different parts of roadway geometry that can tell you, based on the design speed and other factors, how much crown is required, or how high to super elevate, or the allowable rate.
Nice. Thank you for sticking through and watching through that video. I just want to welcome a few of you, maybe two of you, to share something from that long and insightful video. I'm sure that most of you got to learn from that. And I can see Engineer James right there, but I'll ask him to allow one of us to share something before it takes over. So the mic is open, and you're welcome. You don't need to ask for permission to converse with us. You can just unmute, and you can even say hi and share something small from the long video that we've played. I've realized that a number of us have joined, so I just want to reintroduce myself. My name is Engineer Blesius Chelimo. I'm a civil engineer and highway engineer in Kenya. I'm one of the roadsub team, and we are really honored to have you here today. You're not late. We've just started. We played a short video for you guys. For those who were in the meeting earlier, we want to welcome one of you to just share something that you got from the video to those who are not in the meeting earlier. Then after that, Engineer James will take over and he will take us through the horizontal alignment masterclass. Welcome again, and we are honored to have you guys.
Okay, my name is Godfrey Kalendo. I'm a civil engineer, and I'm here in Uganda. I'm a graduate engineer. About the video, I have just joined the meeting, but at least I picked a concept of it. And what I picked from the video is that in whatever we design, especially highway engineering concerning about roads, it should be noted that we mind a lot about the comfortability of the road user, especially the people driving cars, the drivers, even the passengers, because everything that we design along the road is being felt by the passenger or by the driver, being it the speed, the design speed, being it the vertical and horizontal curves. All these are always felt by the passenger and also the drivers, because whenever they maneuver the corners, whenever they maneuver the sharp corners, the crease and the curves, they have to feel that either this road was being designed by someone who maybe didn't do the designs very well. So it is our responsibility as engineers to make sure that we put in consideration that the comfortability of the road user, the comfortability of the driver, the safety of the road user, the safety of the driver is thought about when we are doing the design of highway projects. Yeah, that's the symbol if I picked from the video, and thank you.
Thank you, Engineer Godfrey. You've just gone straight to the most important part of design. As an engineer, when you're doing your designs, we always say that safety comes first. And in road design, we look at the road users, the drivers, the pedestrians, anyone using the road. We must ensure that our road meets the safety for everyone. Thank you for touching on that. And I can see that James is already ready, so I'm going to welcome you, engineer, if you're ready to take us to the next part.
Absolutely. Thank you very much, gentlemen. I hope, thank you very much for hosting the very first session of this masterclass. My name is James Muridi. I'm an engineer, highway design expert from Kenya. I'm happy to see you today. Please see if you can be able to hear me, and loud and clear from you, give me the flag of your country. So just give me a flag of your country. Let's see who is here, where are you coming from. Let's see the patriots in the house. I can see William is saying hello from Malawi. I can see Felix Araka from Kenya. I can see who is that person. Ah, my God. Sherif from Egypt. I can see Bakamoso from South Africa. Ahmed from, this must be Qatar or something. Zim, my guys from Zim. It's always a pleasure to see you. And everyone, I think this is Bangladesh. This is Tanzania. This is Ghana. This is Somali. Thank you very much. Keep dropping your flags. We are patriots here. I can see someone from, that must be Dubai, that is Uganda, that is India, that is Ethiopia, that is Zim, my guys from Zim are like all over the place. It's always a pleasure to see you. I think you guys are shy. Why were you not sharing your takeouts? But I hope as we are going through this session, I want this session to be super open and interactive. Please make sure that you share your points as we go through this program. I would like to hear your perspective, because road design involves many stakeholders, and that is why we want to hear your voice. Just before I go on, I want to make a commitment. Number one, anyway, no promises. This is going to be either one of the best horizontal alignment masterclasses you have ever been into, or the most boring. There is no in between, but I am not committing to any. I'll do my best to make sure that I do what I can be able to do. This session will be divided into 3 parts. The first one is about your voice, your perspective, and your knowledge. And that is why I asked you to be super active in the chat box. The second one will be hard facts. And when we are talking about hard facts, is because we are engineers, we deal with data, facts, principles, and standards and specifications. And then the last bit will be looking at a case study, and then of course, technical demonstration on how we use the hard data and your voice and perspective to give a balanced design. So let's get into it. You will allow me to share my screen. I can see Blasius that we are at capacity. We are at 99. So I think you need to figure out how we can be able to accommodate more people. I'm going to share my screen. Blasius, please figure that out, how we are going to accommodate more people. I'm going to share my screen so that we go through what I had prepared for you. I hope that you are going to follow through this session. I'm going to make it super easy for you. I'm going to use English. You can be able to use the transcription in case something is not clear. Kindly also remember that this recording or this masterclass is being recorded, and the recording shall be uploaded on our YouTube channel. Just in case, or probably you have not checked out the YouTube channel, my team is going to drop it right here in the chat box. Kindly note that the standards and specifications that we'll be following through this presentation are number one, the AASHTO Green Book, that is version 2018. We'll also be having excerpts from the Kenya Road Design Manual, and also we'll be having some excerpts from the Indian Road Congress Manual. The tools that we'll be using for demonstration, that is in part 3. Remember, the standards are in part 2, and then the tools shall be used in part 3 for the technical demonstration. I'll go straight into the very first video, or the first page that we have all seen. And I remember I raised this conversation in one of my LinkedIn posts, and what would you have done in this scenario? And I remember this gentleman from India who shared a picture where there was, a picture of your digestive system. And he gave a demonstration there. For example, if you ate your food directly from your mouth and then it went directly to the other bit, then it would not be useful to our bodies. I think that was one of the best answers that I got from this point. So I would like to know, why did the design engineer make this decision? What are some of the factors that he considered? I want you to drop a chat in the chat box your reasons. I'm going to read them, but I would like to hear two people, one person from North Africa and another one from South Africa. What would you have done in such a scenario? What would have been your perfect design? I want to hear from one person in North Africa. I don't know which country, but anyone can be able to unmute and speak. 1, 2, let's go. This is your voice, your perspective, your decision. Let's get to hear that. What would you have done in this scenario? All right, my guys from South Africa, let's get to hear one more person.
Can I, sir?
Yeah, good evening, please.
Thank you for the opportunity. My name is Anil Kumar Mishra, and I am from Nepal.
Yes.
In Hill Road, this is the very big issue to convert this elevation and calculate to the minimize the minimum elevation and the gradient. In Nepal, the maximum gradient given to us to maximum gradient is 12%, and this may be caused by the elevation difference and the maximum gradient in elevation. 1.2 another point. Let's say the sharp curve is A and the state curve is state point is B, and the elevation difference may be higher than the achievable gradient. So so in my point of view, so the part to avoid that level difference, and they go through this design.
Thank you very much. That's perfect. I like that you quoted figures. Thank you very much. That's a very technical response. Thank you. One more person. Other than gradient, the difference in elevation, what is the other reason?
Hi.
All right. Yes, please.
How are you? From South Africa.
Yes, please.
I'm not gonna give some technical and numbers when I'm in my answers, but from looking at it, I think my name is Cindy, so I'm a civil and environmental engineer. I think
Yes,
some of it
please.
might have also involved the geography and the soil and all of that of the place.
The geotechnical aspect. Thank you very
I
much.
think-
That's another perspective from a materials engineer. Thank you very much. So those are the two reasons. Any other answer that you have will be justified or not through this presentation. Now, the second question is this necessary? Is this zigzagger thing here? Why did the design engineer do all of this? Why could he just have done a straight section in such a place? These are things that I want you to ponder on as we proceed with this presentation. Now, I also sent another one, another picture here that is really thought-provoking. And the answer here, or the question is, what could have gone wrong, or what could go wrong if this design was implemented? What are some of the things that you think could go wrong in this design? What are some of the things that you could think could go wrong in such a design? One more person, I would like to hear that.
Maybe direction of flow and the hierarchy of the vehicle.
Thank you very much. One more thing.
Safety.
Cindy, so here again, I think also when you're looking at the safety side, since we're designing, we have to look into things like safety for the driver and the pedestrian. I think this would be a
Yes.
disaster in an incident when there's an accident.
Okay, thank you. Safety concern. What is the other thing? One more person. Great. Let us now get into this one. So we have seen 3 different scenarios. This is the first scenario. This is the second scenario. And this is the third scenario. So I'm going to start. Where then do we start? Because in our design, it means that we have seen this to be a good design. We have seen how the decision was made. We have seen this, and we have not commented on it. And then we have this, that we have some concerns about it. So let's get into then, where do we start? The first thing, when you're doing any geometric design, you need to follow a certain framework. This framework is a reference from the Ashtor Green Book version 2018. And some of the things that you need to consider when you're designing any road, and this is always the mistake. Most people, when it comes to designing projects, they will jump straight into doing the geometrics. If you jump straight into doing geometrics, you miss a lot of points and you expose yourself to risks that you could have avoided. So what is the exact framework that a design engineer should be able to follow when doing a geometric design? The first thing that we'll be talking about, we cannot be able to cover everything here, but we're going to highlight the most important aspects. The first one is the project purpose and need statement. This is very important because it is going to inform the decisions that the design engineer is going to make. For example, if you look at this picture on our screen here, the purpose could have been integrating different modes of transport in the existing road or right of way. And therefore, the design engineer went straight to incorporating every scenario. We have seen this mostly in developing countries. I saw where most countries are bringing the BRT. And for example, we had one in Kenya. And this was a disaster. It was actually abandoned and it didn't even get to the completion stage. Why? The authority that was implementing the project forced it, even where the scenario does not allow. The second thing would be, what are the existing and expected future traffic operational efficiency? So it is not about designing new projects. It's about how is our project improving the efficiency of the traffic now and in the future. The second thing that, of course, would be of need to be considered is the existing and expectant future crash frequency and severity. So how many crashes are happening at this section? What is the severity of these crashes? The second thing, of course, would be cost. So we would be needing a project. An area would need an expansion of the transportation network, but we cannot meet the cost. So as the design engineer, and of course, transportation economist and many other stakeholders involved, how can we be able to achieve the best output with the highest operational efficiency at the most affordable cost? And then after we can be able to achieve the project, then what are the future maintenance costs that we need to have? So it is not about constructing now, and you've seen this in Africa and across other projects. For example, in Kenya, we have projects that have been constructed, costing the taxpayers billions of money, but then the maintenance is not done or well planned after all. So these are some of the factors that you need to look at. There is availability of the right of way. Most countries in Africa, and actually even in developed countries, they are moving so fast to include or incorporate the different modes of transport. We want to have bicycle lanes. We want to increase accessibility to people with disability. We want to include the commuter rail. Does our right of way allow that? And then if it is not allowing that, can we be able to do land acquisition? In urban areas, that becomes very expensive. Also, in most countries, it becomes a source of corruption. So before the design engineers goes all the way to do the design, these are some of the background checks and considerations that are done before the actual starting of the project. One of the most important aspects that is going to inform even what we are going to do today is the project purpose and need. The purpose and need statement, this is always written in the concept, in the project concept, informs the priorities on what will not be undertaken in the project. It is important to understand that when we are perceiving horizontal alignment or design of any project, we need to know what can we be able to achieve, what can't we, or what will we not be able to undertake in this project. Why am I emphasizing on the project purpose and need? Project purpose and need impacts it, or it is directly correlated with the horizontal alignment of the road. For example, it could be the purpose and the need that we want to undertake a project is number one, to accommodate the future or the volumes of traffic that we have. It could be to improve the safety. It could be to connect some cities with another city, resources and capital, or rather, and labor. So what is it captured in the purpose and the need statement? This one is going to inform the choices that we make in the geometric design. For example, let's say there has been crashes in this specific street, and therefore we create a purpose statement that says we need to improve safety and we need to incorporate different modes of transport in this street. You can see that will directly impact the horizontal alignment and the cross-section of the road. In this purpose statement, we have two sources of data that can inform this decision. The first one is the past performance. For example, what is the crash history? What is the severity of the crashes that has been happening on this street? Is this street able to serve the intended traffic? So in this case, we are able to get information or insight from this data to predict the decisions that we are making in our design. The second one is forecasting of future performance. We can be able to use the current data. And remember, this one is also happens in scenarios where the road is a new road. So if it is a new road, then we need to have transportation economics and planners to be able to predict what will be the future performance in this specific road that we want to execute. So after we have been able to get the purpose and need, remember, we started from the very first point. We are looking at it from a broader perspective. What is the framework that we are having? Then after having the framework, we came down to what is the purpose and need. This one helps us to narrow it down. After we narrow it down, for example, to improving safety, to improving connectivity, to accommodating the high traffic volumes, then we can look at design controls. So what are design controls? Design controls basically are the basis that help us to determine the geometric design elements. What are some of the parameters? I remember I was talking to a young engineer who wanted to join our program today, and he was telling me that one of the reasons as to why he wants to learn and he wants to join this masterclass is to be able to understand, or his experience has been, he is a CAD technician, he is a junior engineer. What happens is the consultant and the senior engineers just gives him parameters and he's like, this is the concept, this is the design concept, this is the design criteria. Follow this design criteria to give me the design for this project. If this is your situation, this is your scenario, or for example, you have always been able to see designs, but you don't know how they have been arrived at. So we are coming back through this program or this masterclass to inform you on how the design engineer arrived at those parameters. So when we look at these design controls, they are also a collection of many controls that you need to look at. But the selection that you're going to make will be informed by the need statement that was previously developed. For example, we have topography and physical features. The topography and physical features are supreme. They impact the cost of our project. They impact the cost of transportation. If it is a mountainous section, there is very little as a design engineer you can be able to do. So it is always about observing and obeying nature. In such a scenario, this is the effect that was happening in the first picture that I shown you. It was the topography was describing that it is practically impossible for you to go through the shorter route due to the differences in elevation. So the consultant or the design engineer could have told you limit, they would say the maximum gradient is 8.0%. That's it. So for you as a technician or a CAD technician, you could be wondering, why did this gentleman say that? This comes from the road design manuals. The second one is environmental consideration. Our objective is always to have minimal impact. If you look at the design that is currently on your picture, it looks like this road was created there. It is perfectly morphing or perfectly merging with the existing topography. The other thing is safety. How do you guarantee the safety of the road users? The other one is road junctions. How do you locate, how do you space, and how do you choose the kind of junction that you have? For example, in the picture that you're looking here, you could be asking yourself, why did the design engineer, of all other intersections that are available, why did he choose the cloverleaf intersection? Why didn't he go for trumpet junction? Why didn't he go for this kind of intersection? So it is important to note that the kind of junctions and the kind of maneuvers that we anticipate along our project road are going to determine or affect the kind of junction that we recommend. The second thing is, of course, the traffic volume and capacity. So this determines the cross-section of the road. Are we going to have 2 lanes, 3 lanes, 4 lanes, 1 lane, or what kind of cross-section are we going to have? And the primary of all is the design speed. The design speed is chosen, number 1, from the functional classification of the road. If your road is an international trunk road, what is the purpose? It is mobility. You want goods to be moved from one place to another as quickly as possible to facilitate trade. So as we are facilitating trade, because that is our role as transportation officers, then how can we be able to ensure safety of the road users? So therefore, we choose a certain design speed that we have. And then over and above that, the most important is the economic and financial considerations. As you're choosing all of these parameters, how do you ensure that the projects that you're initiating are economically feasible and of course can be able to be achieved under the given budget? So this is a broad and a very broad perspective, but then let's jump straight into looking at another aspect. As we look at these different factors that we have, I hope I'm audible. As we are looking at these different factors we need to look at something that is called design flexibility. So the road design manuals are going to tell you the maximum gradient is 12%. But you'll be like, in this scenario, I'm having a sag curve and I'm having another crest curve ahead of me. Will I really be able to achieve the 12%? Is the 12% feasible according to the type of vehicles that will be using this project route? For example, let's say your road section from your traffic service will be used by arterial or rather goods vehicles, transit vehicles. Is it really economically feasible for you to have a maximum gradient of 12% in a road section that is going to have a lot of transit vehicles that are super loaded? Is that feasible for you? So flexibility does not mean disregarding standards. It means making thoughtful decisions to balance performance, safety, and cost of transportation and construction. And as you make these decisions, you need to document it. So for example, the road, for example, this is a very perfect example of design flexibility. If you look at this project or this picture that is on the screen here, we can say the road design manual says we are using a design speed of, let's say, 50 kilometers per hour. And if you use a design speed of 50 kilometers per hour, it means that we are choosing a specific radius of, let's say, 100 meters. Now, let us go to site. This is the site that we have here, this exact site that we have on the picture. Is it possible for you to achieve a radius of 100 meters on each and every of these curves? Is it possible? Most certainly, you will achieve with some, but others will not be able. So what are the decisions are you going to make as an engineer? What radius are you going to use? If the radius is below the given criteria, what are the measures, mitigation measures that you're going to implement in your project to counteract the negative effects that could come? So for example, you find if the radius is too small, you can be able to increase the super elevation at that section. That is just but an example of the sum of the things that could be done. So if you get to make these decisions, therefore, you need to document why the design solution fits the project need. For example, you are justifying this. This is in your design report. You're going to include how is it going to serve all transportation modes. So there are scenarios where you reduce the design speed because there is students or rather school children crossing. You reduce the design speed because you're approaching urban areas. You reduce the design speed because you're moving up in a mountainous section. How will it perform over time? The decisions that you're making, are they going to stand the test of time? How does this align with the available funding? Very important. If, for example, there is a bridge section, would it be worth constructing a bridge, a box culvert, or using another realignment, using another route? So these are some of the things that you need to document. And after documenting this aspect, I don't know, my screen is most moving. Let me see. Something must be happening. Anyway, let me go back. Yes, after now addressing all of these flexibilities, let us go now to horizontal alignment itself. So horizontal alignment is what you see when you're walking on a roadway. It's just what is ahead of you. And I want you to picture the road that you use going to your workplace. What you see when you step on the street is that. And I always ask you, how many turns do you make from your home to your street? I want to see that in the chat box. How many turns do you make from your home to your work station or to your school? How many turns do you make? How many turns do you make from your home to your school? I want to see that. I want to see that in the chat box. I've just opened the chat box right now. I want to see. Let me see. How many turns do you make from your work to your school? I want to see how many of you makes that. So for you to understand now, for you to design any horizontal alignment, you need to understand what are some of the elements that I will be designing. What are some of the elements that are important in my design? So when we talk about horizontal alignment, you need to understand two most important things. Number one, the design elements that you're going to have. And number two, what is the curvature? What is the geometry of horizontal alignments? What do these curves represent? How do they look like? You know, if you understand those two elements, then applying the recommendations and specifications for the road design manuals becomes pretty easy. So let's start with the design elements. When we are talking about design elements, we have primarily 5 design elements. The first one is the straight. The straight is just the straight section. The second one is the circular curve. And the third one is the transition curve. The fourth one is the super elevation. And then the last one is the side friction factor. For this session, we are going to break them down very quickly in an easy way so that we go now to the actual application of these principles. So this is the geometry of an horizontal curve. So this is the straight section. This is now a vehicle that will be moving around this area. So I want you to assume this is the straight section that we are moving on. And as you get into this curve, for the vehicle to be able to negotiate this curve, it will need to have something that we call a transition curve at this point. So the transition curve is going to allow this vehicle to transition from a straight section into this curve without necessarily losing its way to move to this point. And therefore, this means the super elevation is going to happen within the transition curve at this point. So in this case, we have seen the straight, and then we have seen the super elevation and the transition curve. If you move from the transition curve, then you will get into the circular curve at this point. There are critical points that you need to note. For example, is the point of curvature. And the point of curvature is a point at which the vehicle will be moving from the straight section into the circular curve. And then the same thing happens on the other side. It is important to note that when we are doing design of roads, it is recommended that we try to have a symmetrical horizontal curve. When we are talking about symmetric horizontal curve, it's the nature of drivers and the nature of human beings is we are always happy or we want predictability. And when we are talking about predictability is when the road, when a vehicle or a motorist is getting from this straight section, they anticipate that as they get into this curve, they will exit in the same manner within the same constant parameters. It is the same way. Just think how you are moving around a house. If you move in the right, you're expecting that you will move in this opposite direction. If something happens in between, there's a high likelihood of being confused. So as a design engineer, our objective is to try to make sure that our design elements are as consistent as possible. So let us look at what does the road design manual recommend for us to look at as we are doing the design of these elements. It is important for you to know that when it comes to horizontal alignment design, you are only designing these elements. These are the only things that you'll be designing. Interestingly, the side friction factor is already taken care of. So what are you doing? You're only designing the straight section, the circular curve, and the transition curve, and fitting in super elevation to achieve safety. And what else are you achieving? What else are you achieving with super elevation? Safety and the comfort of the road users. Now, let's go to the straight section. The road design manual specifies that when you're having a straight section, look at this road. It's super straight. Straight should not have lengths greater than 20 times the design speed. I know the question that you're talking about is, what about countries? What about flat terrain? What about sections that you have a very straight section? It therefore means you will always note that there is speed limit signs. You will notice that there are some rambo strips and such factors to be able to reduce. For example, one notorious scenario is in Dubai. Dubai, the terrain is super flat, like very, very, very flat. And you find that the design speed for their sections is actually above 130, others are 150, others are 120, depending on different sections and classifications. Therefore, in such a scenario, they have a very strict rule on controlling speed. So if you exceed the speed limit in a section, you are booked. That is one of the mitigation measures because people are notorious. If the speeds, when you have a very strong section, straight section, you risk end light glare. So people moving in opposite directions, this happens, and people say you're banning me. And the second one is, of course, excessive speeding. And then the other risk is when you have straight between circular curves following the same direction, then they should be 6 VD. They should have lengths greater than 6 VD. I always give an example of your eyebrows. And this is one of the easiest way. So if you look at your eyebrows, if we say we are moving from left to right, they are all moving in the same direction. They are moving from left to right. So if we have such a scenario, assume this is the left eye is the first curve and the right eye is the second curve. This curve is moving in the same direction. They are all moving in a clockwise direction. The short straight is your, I don't know what is this called. I don't know. Is it your forehead or something? If you have a short forehead and you have long eyebrows, you look funny. You look funny. You will look funny. It is technically what is happening also in roads. If you design a curve in this direction, and then you have a short straight, and then you have another curve on this direction, it's going to look funny. And what you're causing there is what is called a broken back effect. So you don't want to have such a scenario. You ensure that the straight between two curves is greater than 6 times the design speed. The circular curve, of course, circular curve is a factor. We always measure the minimum radius. And in the minimum radius is a factor of the design speed, the coefficient of friction, and of course, the maximum super elevation. And this is the formula to come up with this. You don't necessarily have to calculate it because we have some tables that gives us the examples. But one relationship you need to notice is the higher the design speed, the greater the radius. The higher the design speed, the greater the radius. If the super elevation is higher, it means that the radius is going to be smaller. It's of course, the radius is indirectly proportional to the super elevation or to the sum of super elevation and the radius of friction or the coefficient of friction. But it is also directly proportional to the design speed at that specific area. So let's say, for example, we have chosen, how do we choose the design speed? When we are talking about the design speed, we need to consider three primary things. Number one is the terrain. Is the terrain mountainous? Is it a rolling terrain or is it a flat terrain? Common sense says if it is a mountainous terrain, we are going to choose a lower design speed. If it is a rolling terrain, we will choose a higher design speed. But of course, if it's flat, we will choose a speed that is higher than the rolling terrain. Now, if that is the case, we need to look at the second factor, which is the functionality of the road. Is it an international trunk road? If it is an international trunk road, what we are looking at is mobility. So we want people to move super fast. We want goods delivered. We want people to move from Abu Dhabi, I don't know to where. We want people to move from Dubai to the other satellite city. So this means we are going to choose a higher design speed. The second is, the last one is, I talked about classification, terrain, and the other one is safety, or also the traffic volume. How much traffic volume are we expecting? If the traffic volume is very high, we need vehicles to move faster so that we don't have congestion and queuing. So those are some of the parameters that we are going to choose here. Of course, access control, is it restricted or is it open? So in such a matter, if we consider those parameters, we can be able to choose the design speed. Let's say we have chosen a design speed of 80 kilometers per hour. If we choose a design speed of 80 kilometers per hour, then the radius will be 350 meters. It is important to note that the above values for minimum are based upon maximum super elevation of 6%. If this is the Kenya Road Design Manual, but if we look, for example, at the AASHTO, this is the American standards, which is a global manual, you will notice that for each of their recommendations, they have super elevations. Someone is writing on my screen. I don't think that is necessary. I don't think that's necessary. The maximum super elevation is 4%. So you can see for factors of a maximum super elevation of 4, we have the limiting values of coefficient of friction, and also we have the calculated radius, and we have the rounded radius. These factors, you can be able to pick them directly here for preliminary design. But of course, as you do your technical design, you can be able to create an Excel sheet to generate all of these factors for you, just to counter check and ensure that you are using the right parameters. But the easier way is always looking at the road design manuals. What you will notice is, let's say, for example, a design speed of 80. If you look at a design speed of 80 and a maximum super elevation of 4%, the maximum radius is 280. If you go for the same at 80, design speed of 80, for a super elevation of 6, we are seeing that the radius is 250. So the higher the super elevation, the lesser the radius that we are using for our section. And then we go to the most exciting bit, the transition curve. So the transition curve is a spiral curve that is applied to effect the transition between two circular curves, or between a circular curve and a straight. If a vehicle, you remember the demonstration, so the vehicle is coming from the tangent in, and for it to get to the main circular curve, it has to go through the spiral. So this spiral allows the smooth transition of the vehicle into the main circular curve. It is important for you to note this geometry and the relationship. Most importantly, it is important for you to visualize. And this is where I always talk about designers. Designers are people who can be able to visualize. When I'm talking about this curvature of an horizontal alignment, or the curvature, yes, of an horizontal curve, what should be happening in your mind is seeing that actual transition of the vehicle. It is only from that point that you can be able to make the right decisions for your design. So this is the spiral. So let us look at what happens at this spiral. what happens at this spiral section. So, of course, this is an example of an actual road, and I would like you to look at it. So, for example, this is the circular curve, and probably from this point to this point, we are going to have a transition, and then we get into the circular curve, and then we are going to have another transition at this point. And clearly, you can see this road on the left, on the right-hand side, it's super elevated. And if you also you go to this point, you can see clearly that the road has been super elevated on this other point. If also you look keenly, you can be able to see also the super elevation is transitioning through this area. Like there is a difference in elevations. So what is the purpose of this transition curve? Number one, they provide a natural, easy to follow path for the driver. Aspiro, the drivers, when the drivers are moving, and this is just like you cannot move from a straight section and then just turn. Even if you're walking, you don't just walk and then make a turn. You need to have a very smooth way to move. And that is what the transition curve does. The second one is to minimize the encroachment on adjoining traffic lane. If there is no sufficient section to transition from a straight to a circular curve, what will happen with the vehicle? It's going to use the extra lane for it to have a bigger radius to turn. So for example, if there was no transition at this point, the vehicle would move outside this lane and get to, or rather from the outer lane and try to, or from the inner lane and try to move to the outer lane so that it can complete the turn. The second one is, of course, provide a suitable location for super elevation runoff. We have seen this is where super elevation is developed. And then, of course, flexibility in accomplishing widening. So if you're doing widening on a curve, you cannot start widening at the start of, or where there is already a circular curve. You start widening of your road at where there is, or rather at the transition zone. So as you transition, let me go here. If you wanted to do widening along this curve, you cannot start widening your road at this point where there is the main circular curve. You start widening your road at the transition so that now as the driver gets from the straight section, they can be able to clearly see that the road is being widened at this area. If you started it here already, it will cause a lot of confusion. And then as they exit this, remember also, if you widen the curve at the entry, if you widen the road at the entry, it is important for you to transition all the way and complete it at the exit. Otherwise, imagine you're going to introduce what we call sudden changes in the geometry of the road. Now, let us move very quickly. I don't want us to spend a bit of time in this area. Of course, it enhances appearance. You can see these roads look super beautiful when there's transition. It's easy, like it's visible. You can see it right here. The other one is the noticeable breaks. So as design engineers, and this is important, you will notice that there are scenarios where you cannot be able to, you want to change. You want to widen, and it's connected with the widening. You want to widen the road, you want to narrow it down, you want to do those things. You can always introduce a transition, a smooth transition to guide the driver from a wider section to a narrow section, from a narrow section to a wider section. These are called giving the drivers perpetual cues and also giving them physical cues. The transition will give both the physical and the perpetual cues. With that transition, you can be able to see that the road is transitioning to a wider section or it's transitioning to a narrow section. These transition curves, of course, they give areas where we develop super elevation. The Ashton Green Book has given, this is exhibit 334. It's giving us some of the desirable spiral length that we need. There is, of course, a calculation where you can be able to calculate according to your design speed. But of course, these are the desirable figures that you can be able to look at. You can always check them out. Then if now you have this desirable spiral length, you will transition now to develop your super elevation. Super elevation is introduced in on horizontal curves in order to counteract the centrifugal acceleration force And this is a diagrammatic expression of how super elevation will be developed along a curve. And of course, how vehicles are going to move through this. So in an horizontal curve, this is the transition that happens. You will start from a normal crown. So the road is, the 2%, the 2%, 2.5, 2.5. I know different countries have different recommendations for the crossfall. And when you start from the normal crown, the crown will be balanced. And exactly at this point, you can see that this is point A, where we have the normal crown. If we go to point B, this could be equated to this point here, the TS. That is the beginning of the transition curve, where we have the tangent in, we have the normal crossfall. And then at exactly this point, this is where the road now starts to, I think my screen was not visible. If I am not visible, if I am not audible, please let me know so that I cannot be speaking to myself, please. So what happens is we are going to have a level crown. So in the level crown, the left lane, and this is always the outside lane, starts to lift slowly. And then after that, we are going to move all the way to the level. Felix, the session is being recorded. This one will be provided. Please don't request. So as we move from the normal crown, we go to the level crown. And in the level crown, this is where the outer edge is being raised. And remember, it is being rotated about the center line. So the center line does not raise. And then after that, we go to this other section, which is a fully super elevated section. And therefore, at this point, we have been able to get to full super elevation into the middle of the curve. Remember that now all of this is happening within the spiral. This is happening within the spiral section. And therefore, this is what is called super elevation runoff. This is super elevation runoff, the entire of it. And then this other section this is runout, this is runoff. It happens on both the entry, that is the entry spiral, and also the exit spiral. And within the circular curve, this is where we have the full super elevation. The full super elevation happens from point C to D. So the entire of the circular curve is super elevated. So this is just a demonstration of the super elevation, and that is the rate. Remember now, as this road is being raised, remember, as this road, the outer edge of the road is being raised or being super elevated, it cannot just be super elevated anyhow. There is, of course, a rate of change. So the rate of change of super elevation is the difference in gradient between the carriageway edge and the rotation axis, which always the center line. And this one is, of course, limited to these values. These values are given to the road design manual. And this is where calculating manually using Excel, I think it's Jonathan and some other guys, we were having this conversation on LinkedIn, that in as much as the Civo 3D is calculating super elevation for you, it is important for you now to calculate it manually using Excel so that you can make sure that within the selected design speed, let's say, for example, we selected a design speed of 80, you can ensure that the maximum change is 0.5. The software will always give any value. For example, sometimes it can give something higher than 0.5 or smaller than 0.5. So what happens is when you go back to calculate the length of these sections, they will not be sufficient. They will not be sufficient. And therefore, you calculate manually using an Excel. And then after you use the Excel, you can be able to counter check that one using Civo 3D. I think this is too much theory for you guys. Let's now dive into doing a case study. In this case study, I'm going to use a very simple approach. Please make sure that your questions are coming in the chat box. I'm going to respond to all of them. I am going to respond to all of your questions today, even if we have to sleep here the whole night. I am ready for that. Now, let us look at horizontal alignment. In this case, I want to go to something that is called contextual application of that knowledge. We have been, allow me to take some water. Great. When we have gone through that theory, that is theoretical knowledge, a lot of theoretical knowledge. And I know you are not looking for that. You have already been able to read that in your road design manuals. You have been able to read that in college. You have been able to read that in all the LinkedIn posts that I've done. The gist is, how do I apply that knowledge contextually to solve specific engineering challenges? In this demonstration, I have 3 case studies that we are going to look at. In these 3 case studies, I have a very simple design. We have an intermediate level of difficulty, and then we have a little bit of more of a complex, and we will be working on the complex. Some of the work here is courtesy of the students that we've been able to train, and therefore I give credit to them because it's not my work. I have some work from Barak Abdallah, Joshua from Abdallah is in Kenya, Joshua is in Ghana, and then these others are mine. Let us look at the first one. This is a typical scenario of a design that I did some years back. And in this design, as you can look at it, we are looking at horizontal alignment design. And let me look at something. I wanted to show the map so that it's easy for us to look at the site. Great. This is a very straightforward design project. And in this project, this is a very simple geometry of the road. You can see this is the existing road project, and the horizontal alignment is not complicated. It is very straightforward. You can see this is a straight section. We'll move from a straight section. We'll get into a circular curve. And then after a circular curve, we get into another straight section. And then after straight section, of course, there is some transition that is happening in between this section. And then there is another horizontal curve, and we have a culvert that is positioned in this area. And then after that, we have another straight section. We curve in another horizontal curve. And then after that, we go straight section and all the way to the last point. So this is a very simple application of the geometric principles. What happens in such a scenario, it is easy for you to implement the specifications that we have. This is a flat terrain. Actually, no, it is a rolling terrain. And when we are talking about a rolling terrain, it's a terrain that has a gradient of, for example, we are looking at from I remember it's from 5% all the way to around 7-8%. Yeah, to 7%. That is more of a rolling terrain. So that is the terrain that we anticipate. For you to determine that, you normally carry out surface analysis, and you can be able to see the mean or the average slope that you have in your entire section, road section. So in such a scenario, you don't have a lot of obstructions. You already have sufficient right of way. So you don't need to go outside the road or rather the specifications given. Let us look at it, for example. I'm going to select, I don't know where is the alignment. So I can go to the tool space. Under tool space, I can go to the prospector. Under prospector, I'm going to alignment, center line, and then I have the main alignment. I'm going to say, for example, select it, and then I'm going to go to the geometry editor. Once I go to the geometry editor, I will have the alignment layout tools with me. And in that case, I'm going to alignment grid view. The alignment grid view allows us to actually inspect the various design parameters that we have. And of course, we can be able to change them, modify them, and inspect them. We can also be able to look at different parameters that we have in different scenarios. So if you look at this alignment grid view, you can see that the design speed that we had chosen for this specific project was 100 kilometers per hour. So for 100 design kilometers per hour, I've told you the scope, or rather the slope, was a rolling terrain. So people have to go. This is also class A of roads. It's an international trunk road when it comes to the Kenyan standards. So the main priority is mobility. People need to go and do business. So that's why we are choosing a design speed of 100 kilometers per hour. Once you choose those parameters, you can see the design speed has been specified here as 100. I want us now to go to the second one, which is the radius. If you look at this one, the radius for the first curve, I don't know, now at this case, anyway, we cannot be able to see this. I don't want to spend a lot of time. If you look at the design speed here, the design speed is 100 kilometers per hour. For our minimum radius that we used for the radius that we used for this curve, it is 1015. If you go to the road design manual specifications that we just looked at, let me just go back to it. There's no arm. If you look at the design speed or the specifications of the road design manual, the Kenya road design manual says that for a design speed of 100, we need to use 600. These are minimum. So with the minimum, we have used 1,000 and I think it's 1015 kilometers per hour. This is also the other point of interpreting these figures. When we have a minimum, it does not mean that your design must be able to use a radius of 100, of 600. You can use another figure that is above this. This goes back to what we called design flexibility. When we look at design flexibility, it is the decision of the engineer to make these decisions on site. So let us look at this specific curve. It is the first curve, and it is starting from kilometer 5 plus 219 to kilometer 5 plus 316. I can be able to close this, and this is the first curve that is in this case. So why did the design engineer, or why did I make the choice of using a radius that is too far away from even the prescribed radius in the road design manual? Number one, when you're designing roads, you need to consider what is called driver behavior patterns. For this one, or the existing conditions is the drivers who are used to this road, they have an existing path that they have been following. It is the same scenario that happens when you're going to your home place. You already have a path in your mind. Interestingly, most of the people and yourself operate subconsciously. So road users, they have been using this project road for this number of years. So what do they know? They know as our road is here. So all they do is just move. So that is the first consideration. So you don't want to align or change the patterns of the road users. That is why when you have a new project road that has been aligned, there is always a rise in fatal crashes and incidences and accidents in the first few months when the road has been opened. Why? People are used to, we make a left here, we make a left. Today, we are making a right. The second one is the right of way. So when the surveyors are allocating the right of way, they also allocate what was existing. So what would be the point for us using a smaller radius just to move the road and we have sufficient right of way? What is the point? There's no point. The other option would be with a bigger radius, it is safer. It is easy for the road, it is more comfortable. I want you to remember this scenario, and I saw this meme. I must post it tomorrow, where someone is negotiating a curve and the curve is tight, and you hold you hold, if you are in public transport, you use your two fingers to steady yourself on your seat as the road negotiates the curve, you know. So in such a wide radius, that is not going to happen. So I'm also taking care of the comfort of the road users. So what I'm saying is, when you are considering design flexibility, you need to think in 4 dimensions. Number 1, technical dimension. Hard figures, like my guy from Nepal told me, 12%, 8%. The second one is safety. How safe? How safe? This means you need to meet the minimum requirements. The other aspect is the operational safety, efficiency and comfort of the road users. How safe is it for road users? The other one is you need to think in terms of what is the existing. You don't have to disturb what is existing, what is functional, what is moving. You don't have to necessarily disturb that. So those are some of the considerations. This is a very simple design. You just hit it and go and move and move and move and move. You are following the existing route. You don't have to think a lot about it. The same thing happens to its also vertical alignment. This is its vertical alignment, and you can see it's a super rolling terrain. But let me close that. Let me go to the second scenario. I want to close that. I want to go to the second scenario. In the second scenario, it's where we also have, okay, this is an intersection. We have a T-junction here, an intersection. And of course, we have done some widening, some acceleration, speed change lanes, and all of that. But I want us to go to a specific point that is of interest. And this is what happened now. Remember, in our first design, we have been able to meet all parameters as per the existing route, as per the existing site conditions. We are able to achieve them super comfortably, very easy. We don't have even to do, you don't need any expertise. You don't need a lot of problem solving. You just follow it. You follow it, minor modifications, and then you ace it. But now we have a scenario where the road is flowing very nicely. Let me actually turn off, anyway, no, before I turn off the maps, I want you, yes, let me turn off the maps first. Allow me to turn it off. Turn off. Oh, after turning it off, I remember I had captured this. Let me delete this image. Okay, great. I have another one here. So this is just an overlay of the image that I had created. So I want you to look at this scenario. So in this scenario, we have an entire road project that is completely fitting into the existing road corridor with minimal encroachment in the parcels of land. Remember, these are people's parcels of land, but we are getting to a difficult scenario here. And in this scenario, you will find that number 1, where the road is existing, now I have to turn on the map again so that I can show you what I mean. Let me see whether it turns off. Oh, great. So you can see where the existing road was moving. This is where the existing road was, this is the original path, and therefore you need to do realignment. One of the reasons why we were doing realignment for this section is this is a very steep section. It's of course, you cannot be able to see it in the pictures. This is a very steep section. And in this steep section, we're having a curve, a sharp curve at this point. So this necessitated the realignment of the section. If we decided to follow this existing path, it would not meet the minimum requirements of the section. That is the first point. In what aspect was it not meeting the minimum specifications? The first one is the existing right of way. So the right of way would not accommodate it. If you look at this magenta line is representing the right of way. And you can see the right of way, it's even, or the existing road is outside the right of way. Number two, this means that the horizontal curvature, that is the radius, cannot be able to fit. That is the second option. What then did we have to do? We had to do realignment of the section so that number one, we can be able to at least fit the geometry of the road horizontally at this section. Either way, we needed to avoid land compensation. We don't want to have parcels of land, or we didn't want to have encroachment. You can see this is the parcel of land on the left, and also this is the parcel of land. My brother, it's not necessary to write on my screen. I'm going to, yeah, please, so that I just complete this. Yeah, thank you. I can probably wrap it if I am able to do so. Yeah, there's no point. Thank you. I think it's a mistake. Yeah, it's not intentional. So we needed to accommodate the road in the existing corridor. So this is where you do realignment. In this realignment, we notice that if we have to fit within the existing corridor, we cannot meet the minimum specifications still. And what are we avoiding? We want to avoid land compensation. In Africa, whenever it comes to land compensation, in most countries, it's a corruption case. The road will never be completed. The land compensation will take years. There will be cases. People will be faking title deeds. People will be overpricing and overvaluing the parcels of land. So we want to minimize that. So if you can't meet the minimum specifications, then what do? You provide the measures. You need to provide mitigation measures. So for example, we say these are slow down, speed bumps ahead, these are signages. We need also to put these, we need to show that there are some humps, and also the same case needed to be done, or we didn't do it on the lower side because this would be a fatal section for the vehicles that are approaching. So this is a second simple scenario where you have not met the minimum specifications, you have different constraints that you need to play, lack of enough right of way, you need to look at safety, you need to have to look at speed. I remember also we reduced the design speed. So I think there is a section where we are showing the reduction in design speed of the section. I think the design speed was lowered all the way from 80 all the way to 50 kilometers per hour, but it was lowered gradually. So this is another scenario where you need to think about it. Remember, as we were doing the realignment in horizontal alignment, there was also a problem in vertical alignment. Look at that very specific section. In that very specific section that we are looking at, let me turn this thing off. In that very specific section we are looking at, where there is a constraint in parameters in terms of horizontal alignment, there is also a constraint again when it comes to vertical alignment. You can see the slope was primarily way above. I remember the slope here was 7.8, which is above the slope that we need to factor in at a design speed of 50 kilometers per hour. So what this means is we have to cut. But as we are cutting, this section and rock outcrops. From just a visual inspection, we end a lot of rock in that section. So this becomes, it is a cut in hand. Cut in hand is expensive and the cost of the project is going to skyrocket. So what do? We have to fix in, I remember for a design speed of 50, the slope that you need is about 6. It's about 5 point something or 6. So you need to play in with these factors. What can I do? What is the amount of cut? Remember also you need to control the amount of cut and fill that you need to have at this section for you to not have a very expensive project. So these are some of the things that you need to factor in, and this is what is called flexibility in design. So what I'm communicating is, it is not in every scenario and every project that you design that you're going to meet the specifications. But now for you as the design engineer, you need to do reasoning, technical reasoning, logical reasoning, providing solutions, being innovative, and document it so that even people who are going to do future maintenance, future improvement can be able to see the decisions that you made. You can be able to predict what are the consequences of the decisions that you make. I am not advocating for disregarding of specifications. What I'm talking about is, you as a design engineer, you're a problem solver. So you need to evaluate the best scenario. This is an iterative process. I remember we did the design for this section for almost 2 weeks, back and forth, back and forth. We discuss. The next day, we come and say, no, engineer, that is not making sense. And then we go to another meeting. No, engineer, that is not making sense. You go, research, do this, do that, do that. And then at the end of the day, we were able to come up with a legible or a logical design that is implementable on site. What time is it? 21:28. And then we are looking at another now, more complex scenario. This is now level 3. We have looked at level 1, we have looked at level 2, and now we want to jump straight into level 3. And I normally tell my amazing engineers, it is not about Civil 3D. It is not about the software. It is not about the software. You are the designer. You are the problem solver. You are the person who is thinking logically to provide solutions that are going to be implemented on site. So let us look at this project. This is from one gentleman, Joshua, and this is actually the project that we're designing in the upcoming course. For those of you who are not aware, this is a 9-kilometer project road. It is here in Kenya. It's actually, it was just under construction. I don't think even they completed it because of land acquisition issues. I told you about this super complicated project. It's starting at this point. This is kilometer 00, and it moves all the way through these. Look at this one. It moves all the way to this other point. So this is a super expansive project, 9 kilometers. If you design this project and you've not aced your game in geometric design, it could be it will be something else. I don't want to know what it is, but it could be something else. So this is the project that we'll be designing. And as part of designing this project, we will be able to see all the scenarios that I've talked about. We'll be able to make decisions. We are going to meet a lot of constraints. I mean, a lot of them in this project. And therefore, this is going to test your decision-making skills. It is going to test your logic. It is going to test how good do you understand the road design manuals and specifications, and how can you be able to integrate them in an actual project. And this is what I train you guys. I'm not training you Civil 3D. You can learn Civil 3D on YouTube. I mean, there are 1,000,001 courses on Udemy, and they even go for $10, and I don't know, 5, 9. They have those offers. I want actually to delete my course from there. It's pathetic. I cannot be offering my value with such competition. It's not worth it. This is the thing. Can you be able to solve it? Can you be able to use the knowledge that you have? So this is it. I want us to do simple design for these sections right here with you, so that you can be able to probably see it. Number 1, I want us to choose the design speed. If you look at this scenario, it would take us a bit of time to do the surface analysis to be able to understand the topography. So I'm going to give you data or some insight on that. So this is a technically very mountainous section. You can see actually even the vegetation cover tells you. And it is also in a section where is it tropical or something, where there is a lot of rain, it's mountainous section and all of that. So this is a primarily mountainous section. It has many constraints. It has a mix of both an upcoming market center, if not a town. I don't want to use a town. And therefore, it means you need to consider also different aspects of how people are maneuvering in this area. So there is that. And then, of course, it has also sections where you cannot be able to meet the specific design requirements. If you also look at it, it is not necessarily an international trunk road. So this is a link road. You can see it's just connecting some local guys here who, this looks like the main road. You can see clearly, this is the main road. It's called Kangema Road. And then if you look at it, it looks like it's connecting to another main road on the left, on the far left here. So this is like a link road. If it is a link road, the class or the classification is a lower standard road. The main reason for that is access. You want to provide people access. There is economic activities. These people need to access market and bigger, blah, 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 all of that. So this means if we are choosing our design speed using the 3 criteria that we said, we would choose a lower design speed. So let's say, for example, we are choosing a design speed of even 60 kilometers per hour or even 50 kilometers per hour. Of course, this is a subjective process. I'm just using some figures so that we make it quick. Of course, you need more data to choose the design speed. Now, let's jump into the road design manual. The road design manual says for a design speed of 50 kilometers per hour, you need to use a radius of 100 meters. That is the minimum radius. Great, that's fantastic. So we have the design speed and we have the parameter of the radius. Let us look at the other aspect. What would be our minimum undesirable spiral curve length? So if you're looking at spiral curve, for a design speed of 50, we'll be looking at a spiral of radius of 28. So note that down. We're having a design speed of 50 kilometers per hour. We have a radius of, I forgot it, 100 meters. We're having a spiral length of 28 meters. Super elevation, of course, most roads in Kenya, Kenya Road Design Manual says the maximum super elevation is 6%. So you don't have even to think, is it 6 or 8? I don't remember. Anyway, wherever. The other one is the straight section should be equal to 220 VD. And remember, if we have 2 curves moving in the same direction, we need to have 6 VD. You need to note down all of those parameters before you go to design. Secondly, I would want to give you a refresher of the geometry of the horizontal curves. We have the tangentine. This is the straight section. We are going to have an entrance spiral. It is represented as LS for the length of the spiral. And then we have the main curve, the exit spiral, and then the tangent out. Remember, our goal is to have a symmetrical section, which means the spiral at the entrance spiral should be equal to exit spiral. That is an ideal scenario, but it may not always be able to be the case in every place. So let's get it. Let's apply that, my guys. Now, how do you do that? So we are going to home ribbon. And a home ribbon, I'm assuming that you're familiar with this one. If you're not, we are going to take care of you in the program. Worry not. I hope you've applied for it. We're going to be doing so much. If you would want to apply, actually, I think my guy should be able to send a link so that you apply and join and get to learn this in detail. We are going to the home ribbon. And a home ribbon, we're going to create a design. And a create design, we'll find alignments. There are 1,000,001 ways, not 1,000,001 anyway. There are many ways to create an alignment. And the first one for designers is always to use the alignment creation tools. So I'm going to select the alignment creation tools. In the name, I'm going to name it, let me say, main road, just to name it. Remember, you use official names. The second one is the type of alignment is the center line. The start station, I would want it to start at kilometer 00. But of course, if it is starting at kilometer 10 or whatever, you can be able to modify that at this point. The second thing is the alignment style. I'm going to use proposed. And then the layers and all of that, I'm going to retain the labels and the C-road. I'm going to retain that. But over and above that, I have something that is called the design criteria. So in the design criteria, this is where you set now the standards and the specifications that we had talked about. And the first one is the design speed. So we have said that our design speed is 50 kilometers per hour. Someone is, you can mute, please. Thank you. There's the starting design speed. We can choose to 50 kilometers per hour. Remember, this is for example, and then make sure that you tick the use criteria based design and use criteria file. This one has the design criteria. This is of course ASHTO, and you remember we are already using the 2018 version, so you can select that and then we open and make sure that's right. The maximum super elevation for this section, you can see for now, the maximum super elevation was 4%, but this one should be 6. This one is going to help us get the minimum radius and also attainment method as per this. I'm going to uncheck the design check criteria because we're going to take that later on and then press OK. Once I do that, it will give me the alignment creation tools. I'm not going to go so much into detail on these, but the first element is always to create the tangent, and this is the straight section we are looking at. So I'm going to use a tangent with no curves, and I'm going to come to this very specific point here. This is the start of my alignment. When you're designing your road, the objective is always to follow the curvature of the existing center line. Remember, we are following through the behavior of the road users. You don't want to change things abruptly and now. Also, the right of way is restricted. So I'm going to make my judgment where my right of way is. I'm going to select to that point. I am going to turn off the map so that you can be able to see it more clearly. If you look at this, this is my alignment. I've made a decision that this is where my straight section will look like. Remember, you are allowed to deviate a little bit from the center line just to make sure that you align the section. This was a mud road, and for example, now it was not very straight. So this is the first tangent in. What we need to do is the tangent out. So I'm going to go back to tangent, now curve. Remember, you need to follow the direction. We started from left to right, and therefore the software expects us to move from left to right. I'm going to make another judgment where I see my straight section, and I think my straight section starts from somewhere like here, all the way to somewhere like, let me say here. Let me just put it there and then press enter. So in such a scenario, I already have the start and the end. I have noted that the alignment style here is a bit, the color is green, and even what we have here is green. So let me just make it red so that it's easy for us to, distinguish. No, let me make the spiral that, and then make the curve magenta so that it's easy for us to distinguish it. Great. So we can be able to see the first tangent, the first straight section, and then also we can be able to see the second straight section. So what this means is in between here, we need to accommodate the spiral where super elevation runoff will be developed. And then for this part, and then a circular curve all the same. Remember, our radius was supposed to be 100 meters. And sometimes it's difficult for you to see or to know what to do. In such a scenario, I recommend going to the home ribbon, and you can be able to approximate the radius that you have at this point. So I can go to draw. Under draw, I can select the 3-point arc. So I'm going to select, for example, the 3-point arc. In the estimation, this is how we estimate. And this is because you are a beginner. As you do this over and over again, you can be able to figure out the radius that you need. because of experience. But for a beginner, you can be able to approximate the radius of your section. The first thing is I'm going to skip, remember the spiral was supposed to be 28 meters. So I'm going to skip like 2 points here. Remember the intervals for picking these survey point or the center line point was somehow 20 meters. So I can be able to skip 2 and then start from this point, probably have my arc from there, and then 2 from this other point. And this would primarily mean that is, for example, where my circular curve is. What I am doing now is I am actually replicating the geometry of an horizontal curve. This, as a beginner, makes or trains your mind to predict. You know, you're training your mind to predict and anticipate, to predict. When you do this, you can be able to learn faster. You can be able to predict even without necessarily estimating. So that's what I've done. I've selected this one. I have my straight section there. I have my straight section there. And at least I have my circular section. And then I've left some gap for the spiral and then for the spiral. So what do I do next? I can be able to check, to go to properties and know the radius of the circular curve. I go back to the home ribbon and the very first palette panel, I can select on the properties and I can see, for example, the radius for that section is 361 meters. So I know the radius that I approximate. Remember, this should not be a fixed figure. We are just approximating. So we roughly it's between 360 meters. So what do I do next? I go back to the alignment layout tools. And alignment layout tools, there is this section where I have the spiral curve. This is the type of curve that allows us to have this connection where I have the straight, the spiral, the circular curve, the spiral again, and then the curve. So this gives us that complete option. It is important to note that you can have many other connections, and they are actually listed in the road design manuals, where the connection between the straight and the circular curve can have, you can move directly from the straight to the circular curve, and those other connections. But the connection that is proven to be to improve safety and easier to use, it is where you have the straight and you're using the free spiral curve spiral between two entities. So in this case, if you go to the spiral curves, you will find the free spiral curve spiral. Free spiral curve spiral between two entities. When we are talking about two entities, the two entities is the first tangent and the second tangent. And then the rest is what we have mapped out. So we select on that. The software now, the command line. This is where you need also to be very attentive. The command line is asking me to select the first entity. So I'm going to select this as the first entity. And then it's telling me to select the next entity. And I will zoom in to where I have my next entity. The curve, it is asking me for solution angle for the curve. The curve now, there are two types of solution angles. Number one is one that is greater than 180 or less than 180. If it is greater than 180, it means that is a loop. If it is less than 180, it means now it's a semicircular curve. And this is what we have here. So we are going to select less than 180. The next thing is asking me to specify the radius. And I remember from our estimation, the radius was 360. So I can use something that is slightly below, let's say 350, press enter. And if you look at it, it is going to ask me specify the spiral length. And my spiral length from the road design manual, it was telling me to use around 28. So I can be able to use something like 30. And then if I do that, you can see it is already giving me an example of how the section will look like. And then remember, it's a symmetrical section. I use the spiral in 30. So I'm going to use the spiral out 30 as well, and then press enter. Press enter again, and I will have my curve right here with me. So I can be able to freeze some of these elements. For example, I can be able to freeze this one. I can be able to freeze all of that. And then I'm left with the section. So if you look at this, I'm actually going to delete, okay, let me not delete that, because if I delete them, now I'll be misguided. So if you look at my curve, let me go to, yeah, I can delete this because of interest of time as well. I can be able to delete all of these elements. So this is now my curve. And if you look at my curve, I have my straight section, which is in red. I have my spiral section, which is now in cyan color. I have my circular curve, which is in magenta. And then I have my whatever section that is in cyan again, and it repeats itself. So all I need to do is replicate the same thing over and over again throughout the entire section. Suppose I would like to change some parameters. And why would I change? I am going to visualize this, and that's why we love using the spatial manager, so that at least we can be able to make decisions on site and be able to visualize what is happening. So if I look at my design, the center line of my roadway is somehow towards the edge of traveled way. And therefore, this means I would need to move it. So in such a scenario, I have to, to modify the location so I can move it a little bit to that point. I can be able to move it also at this point so that I don't have, I don't have my road towards the edge. This is why you design on real time, so that not that, the design that you have can be able to fit exactly on the site conditions that you have on that specific scenario. So I can move this probably to some point like there, and I can see now from the visual inspection, this is great. Then suppose I would want to change the parameters. I'm going to go to the alignment tools and then go again to the grid view. And once I go to grid view, I can see my design speed has been allocated here. I can be able to see the radius of my curve, the radius of my curve. You can see when I select where the radius is, the curve has been highlighted. Check that out. It's the one that is in red. And if I wanted to modify it, so for example, let's say I want to make it 300, you can see it's becoming steeper or more, yes, more steep, gentle, steep. I don't know which is which. If I want to make it more gentle, I can increase the radius to 400 or whatever. Remember also, if I want to change the length of the transition section or the spiral, I can make it 40. That's it right there. I can also modify this to be 40. We'll be looking more into details of why I'm modifying this and the rationale behind it. Remember also, because the software is coded according to the ASHRAE standards, it will give you the minimum spiral length. So you can see the minimum here is given as 19. This one is given 19. We'll also be talking about the parameter A and what it means, and all of these other parameters. We'll also be looking at the tangency constraint because you need to maintain tangency of your road. So once you're done with your design, let me look at this. You can be able to close every time you're done with your grid alignment grid view. I don't know what is wrong with it. You can always close, and then also you tap it off in that manner. So you can save your design. If you need to start your design next time, am I still live, really? Blasius, am I live?
Yes, you are live.
Okay. Thank you. Thank you. So if you want to come and start your design next time, you're going to select the alignment. And once you select the alignment, the contextual ribbon will change, and you can start with geometry editor and continue with your design. You don't need to create a new alignment, and then you can be able to start right there, right then. So this one, we are going to start next time. I hope we are going to go through that. And this is a complete design. Like, for example, that participants in the program have been able to do. Let me, for example, maximize these. So this is the horizontal alignment. This is vertical alignment. This is the cross section and the assembly. Let me maximize this. I don't know. Oh, we used to do what? Yes, maximize this viewport. And I can show you some of the designs that our engineers are able to generate. This is the complete design of the road section. This is a very, very, very well and professionally done design. You can see the corridor has been modeled, the road section. We have all the parcels. We've been able to map out the parcels, and we have made sure that our design follows through the existing corridor. This is the same project for those of us who are already enrolled in our program. This is what they will be working on. We'll be making these decisions. And once we make your decisions, we are going to give you feedback to make sure that whatever you're doing also is something that is right and correct as you proceed with your learning journey. We have been doing this for quite some time, and I would like to invite you guys to join in so that we learn and grow together. These are some of the output that also we have earned from our engineers. You can see this was from Simbarashe. I think it was from some other cohort. This is the plan and profile. You do some professional work that you get to do and output out there. So this is an actual design like you could be doing on site, in your offices, and all of that. So I'm inviting you guys, if you would want to learn actual road design. I'm not training you on Civil 3D. You can learn Civil 3D on YouTube and those other places. I am training you the art of geometric road design. And that is what we're going to be doing. We will be starting on April 7th. It's going to be an exciting journey for 5 weeks. And I hope that you can join us. If you would like to apply, I know my guys can be able to send you a link. This is going to be super exciting. I always I say that whatever I'm doing, I do it as if I'm doing it to God. And my team also marries the same philosophy. We are here to serve you and do you right. So if you want to learn practical road design as it is done by professionals, if you want to improve your problem-solving skills, if you want to improve your collaboration, you work with engineers, you put in the work. And if you're not ready to do the work, please don't waste your money paying for this program. I normally tell people that, and they say I am arrogant. I don't know which could be the definition, but I always tell people the fact. I am not, or we are not in a business to make money from you people by promising you things that we can't do. We are not in that business. We are not also in the business of selling certificates. We are not in that business. So if you're not ready to do the work, if you'll not be available, you can always wait for the next program. This is always my honest opinion and my honest advice to people who come to our programs. And even for those who have already paid and those who have already enrolled, come and do the work. We said stop watching and learn, start doing, start designing. That is what matters. You can only become good. Imagine you are watching workout videos. Even if you spend the whole of your lifetime watching workout videos, you will never have six packs. You will never build muscles. Why then do you think if you watch videos on road design, or you watch videos on Civil 3D, or you watch videos on Revit, or you watch videos on whatever concept that you want to learn, why do you think you're going to learn it? My beautiful, amazing people, I'm calling you to come and do work. Come, let us go to grow together. That is the only way we are going to develop our skills, our countries, and even the people who come after us. We are a young generation, and we are lucky to be here. We are lucky to have these softwares, these tools, this knowledge. We are lucky to have internet that is connecting us from different countries. We can think and reason together. So this platform is not for me to be doing these things. This platform is for you to grow your skills, to connect with people worldwide, to make friends. I now have friends. I remember I was talking with someone and I'm like, I have my friend in Cape Town. I have my friend in Joburg. I have my friend in Kampala. I have my friend in Addis. I have my friend in Accra. I have my friend in Cairo. So that is what I want us to do, to create a global community where we can learn, grow, challenge each other. I am not a pyramid of knowledge. I've also been guided. I've also been helped, and I want to help you. The program is only $75 so that we grow, we learn together. So you can be able to pay today. We have different payment methods. You can join us. We are an Autodesk certified training center. So our certificates are recognized globally. I was talking with one guy, he is from Ghana, but he did the program when he was in Japan. And he told me he has secured a job in Japan. And the program that when he completed, he is called Latif Suboy. You can check him out on he's a brilliant guy, super brilliant, super smart, super smart. That guy is super smart. And he has got secured a job in Japan. Probably will even get payment better than myself. I mean, this guy is doing better than me. So that is what I do. I would be happy if you come and learn and actually explore opportunities that are outside what you can be able to access. The program is going to run for 5 weeks. The reason as to why we have set it 5 weeks is so that you get time to do work, experiment, practice the skills, and implement this knowledge. You bring it back, we give you feedback, you work on it, you work on it, you work on it, you work on it. So imagine like you have a personal coach who is taking you through the process. So I'm super happy, and this is always my hope. This is my family. You're my guys, and I want us to grow and learn together. Thank you very much. I am open to questions in case you have something. The recording will be posted.